voltages, so above 0.8 volts, this platinum can react with oxygen, forming so the platinum side, and so partially blocking the catalytic side of the fuel cell, and so increasing the oxygen transfer resistance toward the active side, and so in the end, the overall performance is of the compound with respect to what theoretically conclusively defined. So defining a P/T/X convergence ratio factor that ranges between 0 and 1, where 0 is the ideal situation, so no platinum oxide are produced, and 1 is the worst case ever, so the entire catalytic sides are covered by platinum oxide. We take into consideration that the formation of platinum oxide follow our normal equation, so we compute the reaction rate of the reaction, and in using this factor inside our Butterworth equation, we were able to take into consideration this relation. Moving now to the validation of the methodology, we have applied the methodology for validation to a case study to a zero gradient cell harbor. This cell harbor has been developed and tested internally at Politecnico di Milano by MRT Lab Laboratory, and it consists of a parallel channel configuration, and it's called the zero gradient harbor because it has been built in order to obtain homogeneous conditions, homogeneous particle conditions across the channel length of the cell. So the only gradient operating conditions are measured in a through plane direction. Then we have, in order to account for this device in open form, we exploited the periodicity of the field, and so we just modeled half of a single channel to reduce the computational cost, of course. And as you can see, we needed a very high refined mesh in the porous media. So here in the gas diffusion layer, for example, in blue or in orange, we are speaking about cells of some micrometers length due to the complexity of the phenomena occurring in the porous media. So that's before condensation and diffusion of reactants through porous media. This fuel cell has been tested in these operative conditions, so with high turbidity ratios and high pressures both at the anode and at the cathode side. And in this slide, you can see the polarization curve of the fuel cell. So it's the curve of performances of the components. So similarly to a torque curve for an internal combustion engine, on this curve, you can see the performances. So the current that is produced by the component divided by the active surface, so the surface where the reactions take place, and the y-axis instead the voltage measured across the fuel cell. What we can see is that with the methodology used in OpenFOAM, we found a good agreement with experimental results. And if we plot this curve in a logarithmic scale, in order to better see the behavior of the curve in this region, so at high voltage and very low current density, we see that thanks to our implementation, so the platinum oxide formation, we were able to have a good description of the performances of the component with respect to the original library where the degradation mechanism was not taken into consideration. Once the methodology has been validated, then we use this methodology to carry out a parametric analysis. So starting from baseline configuration, we decided to change the rib to channel ratio, where rib is the length of the bipolar plate being in contact with the porous media, and the channel is the channel 8. And so we tested two different configurations, one with a longer rib and one with a shorter rib. And what we have found out, speaking about performances, is that the main difference is found out in the so-called mass transfer region, so where the production of current is very high, so the consumption of the reactants is very high, and the worst performances have been found out for the variant 1 configuration. In fact, the one with the longer rib as expected. In fact, with this type of geometry, we have a lower diffusivity of the reactant from the channel toward the positive media, and so we have lower performances. And we have found out is also looking at the concentration of reactants across the channel, so across a cross-section of the channel. What we can see, if we compare the two opposite configurations, is that in where the rib is longer, of course, the concentration of oxygen is lower under the rib in case of low voltages, so where the consumption of reactants is higher. So we have lower oxygen transport for longer rib, but not only, also the water that is produced on the cathode side encounters more difficulties to diffuse from the porous media where it's produced toward the channel. And so we tend to have the blockage effect even by the condensed water. And so more decrease of performances for the variant band configuration. So with this CFD analysis, we have found out what we expected from literature, and so that the rib to channel, and especially the rib length, must be chosen as a trade-off between current conductivity, so here is where electrons move to move inside the polar plate, and reactant diffusivity. Then, with the same methodology, we tested a more complicated geometry, so no more a parallel flow channel configuration, but a serpentine flow field. So this type of geometry consists of 3 channels with serpentine flow geometry, as I said before. We needed a computational domain of obviously larger, so more than 2 million of cells. And since the analysis was carried out considering only low current density, for this case, we assumed a single phase at the cathode side. So the condensation of water has not been modeled in this case that I will show you. The operating condition of this fuel cell were a little bit different from the previous one. So we can see a lower stoichiometric ratio and atmospheric pressure in the air and hydrogen channels. And what we have found out in our methodology is, even in this case, a good agreement with experimental data. Now I will show you some visualizations coming from this study of this particular geometry to show you what you can compute with this methodology, because we are not only able to compute the overall performances of the fuel cell in terms of polarization curves, but also in plane distribution of different physical quantities. So, for example, here you can see pressure and velocity. So, as expected, of course, the pressure decreases from inlet to outlet, and here you can see the accelerations in the fluid due to this complex geometry of the channels. More interesting are the in-plane distributions of reactants. So in this slide, you can see hydrogen-oxygen distribution, so at the anode and the cathode, and we can see, as expected, a consumption from the inlet to the outlet. And more interesting is the concentration not only in an in-plane distribution, but also in a through-plane distribution. So as you see in these images, you can see how the diffusion of the reactants affect the performances of the fuel cell, because in fact, you can see that here we have some problem with the diffusivity of oxygen under the rib. And from the distribution of reactants, of course, we obtain also the distribution of temperature and of the produced current density over the membrane surface. And so we can see that where the current produced is higher, of course, the temperature that is computed is higher. And this could be pretty interesting in case of this analysis of degradation mechanism, because, as I said at the beginning of the presentation, water management is a fundamental parameter to be taken into consideration, because if we have some regions in our fuel cell where water concentration is too low, we can have some local hotspot arising, and so some portion where the temperature increases a lot. And so with this methodology, we could detect the point on the fuel cell where a degradation mechanism could happen. So coming to the conclusion of this presentation, we have seen that using a CFD methodology, but with an open source code, we are able to implement different degradation mechanisms, and it could be very useful in order to properly predict the performances of a PEM fuel cell, and we are able not only to compute the overall performances of the polarization curve, but of course the through plane and in plane distribution that could be very interesting if you want to optimize the component, and so in the end try to improve the performances of the component. As the next steps that we want to carry out to take is the study, for sure, of new channel geometry, and so not only perfectly parallel channels configuration as the one that we have seen in this presentation, but we want to implement some geometry variations. So, for example, wave-shaped channel or taper channel, in order to improve the diffusivity of the reactant toward the active surface area, and try to correlate how the change in the geometries can cause a change, and we hope an increase of performances in the PEM fuel cell. And remembering what I said at the beginning of the multi-scale about fuel cell, we would like also to move to the device scale. So moving from the channel scale, as we are focusing now, to a device scale analysis to treat the fuel cell stack as a whole. With this, I conclude, and so I thank you for your attention.
So thank you, Margherita, for your presentation. Now we have time for questions. Can start with just a question to, let's say, both guys. You have shown us a very detailed simulation, 3D simulation, but we know from literature that we can apply also for the study of fuel cell some other simplified approach like 1D. How is the relation of between the result that you can get with the detailed 3D and the result that you can get in 1D, also in terms of computational time?
Of course, computational time is higher with a 3D analysis, but yes, we have examples in literature of 1D analysis, and they are pretty good to study the consumption of reactants from the inlet to the outlet, for example, or the performances of the component. But of course, due to the 1D model, we are not able to study in detail the diffusivity of reactants, for example, in the rib, under the rib, so in the porous media. And of course, a 3D analysis can give interesting insights for the study of the degradation mechanism due to an in-plane distribution of, for example, reactant concentrations.
And if you think to, let's say, the outcome of the 3D analysis, what is, according to you, the most important part to work on? So the most important problem to solve, let's say, in fuel cell that could be mounted at the device scale on a propulsion system?
I mean, as I said at the beginning of the presentation, water management is a critical aspect for these components, for the degradation. And so, of course, a very important aspect to be investigated with the analysis is a correct implementation of condensation model in order to have a proper computation of water distribution inside the membrane, but not only inside the membrane, inside also the porous media, and so to have a proper description of the device operating conditions.
Thank you. I don't know if other questions from the audience. If not, we can thank you again. And we can switch to the next presenter. Okay, So the next speaker is Professor Montenegro that will present the work development and application of a DCFD framework for the simulation of fully coupled electromagnetic and heat transfer process inside the electric motor. So Gianluca.
Thank you, Augusto, for your kind introduction. Ladies and gentlemen, good afternoon, let's say almost evening. Thanks for staying until now, attending the conference, even if you can feel the flavor of electrification. This causes a little bit of fear in people working on combustion, but I mean, it won't be, let's say, too much. So I would like to start, first of all, thanking the contribution of the co-authors of this work, which are Augusto Della Torre and Rachele Zamboni, who did basically her master thesis project with us, helping us in the implementation of the model that I'm going to show you. So in this presentation, I will just give you a brief introduction of explaining the motivation of these developments. So I will pass to the description of the multi-region electromagnetic solver that has been implemented along with the mesh motion. And then I will show some mesh generation and simulation example for this type of application. And then I will move the focus to the analysis of the cooling system modeling. So not only what is inside of the electrical motor, but also what is outside, so that must perform the cooling of basically the electric oil that cools down the electric motor, which is, let's say, a hot topic since it brings with him, let's say, problems of compactness and lightweight. These are the most important concern in this type of application. So the motivation and the background of this work are basically the fact that we see that the electrification is coming into the field of internal combustion engines. So frankly speaking, it's an occasion to widen a little bit our investigation field, and so to, let's say, to decrease to increase the opportunities of application of the CFD, basically. And that's why we moved our focus to the modeling of this type of engine, which are basically, well, a complex system with moving parts, with issues related to the temperature that can reach, since the temperature range must be limited. Otherwise, there will be compromise in the performances, because the permanent magnets usually feel the temperature, the increase of temperature. Then in these devices, we have also cooling systems inside of the shaft, where you have the moving components, and also outside for the cooling of the external part. And then we have heat losses that are basically sources of heat that are generated inside of the motor. And then a cooling unit, which is, as we said before, has some compactness and lightweight requirements, which for application for, let's say, sports car with high-performance car based on the electric traction is a major concern, since the volume that they occupy is, let's say, in contrast with the volume and the weight occupied by the battery. And this is an aspect that is not negligible. Okay, this work goes under the library that has been developed, the LIBA-IC, LIBA-IC. It's for internal combustion engine, but this is like the dark side that is moving, trying to occupy some space. But as you can see, there is also the electrification symbol in the C of the logo. So this is a reason why we have the modeling of the electric component. So as Tommaso said, the library can perform any analysis of internal combustion engine, internal management, analysis, simulation of fluid machine, complex fluid machine, and also after treatment system porous media, and also fuel cell, as we have seen, not in the library, not in the LIBA-IC, but also electric motor and cooling of battery. So what have we done in this field? Well, we have taken an old engineer, mechanical engineer, and said, okay, let's see what are the equations that we need to deal with to model the electric motor. So we saw the Maxwell, the set of Maxwell equations, and these are basically the set from which we started, in which we have a relationship between the magnetic field intensity, the magnetic flux density, the electric field intensity, and the electric flux density. Sorry, it's always difficult to associate all the numbers, all the the names to the variables. But we have this main relationship, and then a constitutive relations that are basically linking these two these quantities between them. Then we did the approximation of steady state problem, which is assumption that is done in the application field of these devices, and then along with this steady state assumption and relying on the fact that the curl of a vector can be discretized in this way, and relying on the Coulomb-Gauge theorem, which states basically the free divergence of the vector potential field A. Well, in this we arrive at this simplified version of the equation, in which we finally arrive to basically a diffusive equation. Diffusive equation that can be applied to different regions. In particular, we have solid region made of ferromagnetic or diamagnetic materials. The solid region in which we have the permanent magnets, so we have a residual magnetization of the element. And then we have fluid regions in which we do not have any magnetization, and then non-magnetic regions where we have the current that flows and in which we generate a magnetic field. So for the solid region, ferromagnetic, diamagnetic, or for the permanent magnet regions, we have also models for taking into account the iron losses, so losses due to the currents that are generated into the material due to the variation of the magnetic field, and also Joule effect losses due to the fact that we have a current into the material. The solver is structured in such a way that we started from an existing solver in which we have let's say a CHT structure. This has been included in this solver because we wanted to have the CHT facility in order to take into account the heat transfer. So it's a multi-region CHT and with moving mesh. So the moving mesh, at every time step, the mesh is moved with the traditional libraries that are implemented in OpenFOAM, and we have added the equation for the electromagnetic equation. So we have at every time step, after some initialization of the properties, because the residual magnetization must be imposed, we have the solution of the electromagnetic equation for the permanent magnets, for the non-magnetic materials, for the fluid, and also for the solid material. In this case, we have boundary condition in order to interface all this region with the vector potential that has been chosen for the solution. The vector potential is variable A that has been chosen to model the magnetic field. We are based on the solution of this equation. We calculate the electromagnetic losses, and the electromagnetic losses have been included in the CHT equation as a heat sources for permanent magnet, non-magnetic, or for all the regions of the electrical motor, and these regions are interfaced with boundary condition on the temperature. So we have a similar treatment of the boundary condition for the magnetic, for the vector potential field A, and also for the temperature. So the test case that I'm going to show you is just a test case that we produced in in-house because we have some confidentiality issues for all the material that we are modeling in the context of funded projects. So this is just an example of how the solver works. So we came out with a permanent magnet synchronous motor, an example in which we have 6 windings for the stator, and then we have 4 permanent magnets here in the rotor. Then we have a shaft inside, and the shaft also has a, let's say, a U-shaped path for the cooling system. And then there is also an outside cooling system, which in this case has not been modeled. We have generalized the process of making the mesh, in which we have a parameterized block mesh that produces a background mesh for the rotor. So we have an application that produces this mesh, and then it is parameterized, so it can be this way or this other way, or with a different number of permanent magnets. And then for the stator mesh, we started with a structural block mesh that has been let's say, shaped to the real geometry by the use of Snappy X-Mesh. Similarly, this happened to the shaft device, in which we have the block mesh, the background mesh, that can be shaped to the real geometry with a U shaped pipe inside, with a fixed and also a moving component with the use of Snappy X-Mesh. So this basically is a fully parameterized step that can allow us to produce different sized motors. The final step is to try to interface all these blocks using also non-conformal coupled patches or AMI, depending on the version of OpenFOAM that you're using. So this is the outside view, and this is basically the clip of this motor, in which we have all the components defined here. So the windings that you see here are the windings in which we have the current that generates the magnetic field. So this is an example. Well, the mesh is moving correctly. Okay, this is an example of the magnetic flux density field that comes out from the existence of permanent magnets, and also for the existence of the windings that are generating a magnetic field. You can see also the interference, so the interaction between the magnetic fields, and then it is possible to see that the magnetic fields changes when the permanent magnet faces a different winding section. You see here some pixelization, which is due to the fact that we have used a very coarse mesh in order to have, say, results quickly that can show the magnetic flux density. And also it is a problem also of an improvement that can be done to the boundary condition of the vector potential between 2 different materials. So here I need to enforce the starting of the animation, and here we see the losses, the prediction of the losses. So iron losses and Joule effect losses. Joule effect losses are visible here, the windings, and iron losses are visible here in the core of the material that constitutes the rotor, and also in the permanent magnet. And here is a view of the magnetic field that is generated by the windings around the rotor. Then here again I need to start the animation. Then here is the effect on the temperature field. So we needed to hide the temperature level of this motor. This is the effect on the temperature, and we see that the windings are heating up, and then also it's heating up the rotor, which is cooled down by the U-shaped pipe that we have inside here. And here you see the U-shaped pipe has a fixed part in the core, and then a rotating part which is fixed with the internal part of the rotor, and produces this swirled flow that goes in this way. I don't see anymore the laser pointer. that produces this swirl effect that goes in this direction, then turns back to go to the cooling unit. So speaking of which, what we have next to this is the cooling unit. The cooling unit is usually made up of a plate, an ensemble of plates, of cooling plates, with the two fluids. One is the dielectric oil, basically, and the other one is the cooling water plus glycol. Basically, usually we have this type of fluid. And then for the oil, we have usually dimple plate, and for the water, we have this kind of turbolator with fins that you see here. These are the example of the two geometries, and then this is the plate that is piled up in a full-scale cooling device. So in this field, we have applied our methodology. The methodology is the same that we have used for the simulation of the after-treatment devices, in which we have a modeling at the micro scale of what is the flow here in the offset strip fins turbolator. So we have the simulation of a microstructure here, and then from the microstructure we extract the information that can be used as tabulated maps of what? Of flow resistance and also of heat transfer, or let's say Nusselt number. And then from these tables we can perform full-scale simulation where the microstructure of the turbolator, or the dimple plates, or the offset strip fins are modeled as a porous media without, let's say, the subgrid definition of the geometry. Then, so we upscale this in this way to this at this level, and then we can pile up every plate in order to do the simulation of the whole heat exchanger. This is useful since it is possible to do the optimization, and the optimization means optimization of the heat transfer and also optimization of the pressure loss. Okay, sometimes depending on the application, the pressure loss is a weak constraint, so it may be, let's say, neglected because maybe they are using certain type of pumps, and the benefits of having a reduction in weight and in volume is more than, let's say, having a low consumption from the pump side. So coming to the modelization of the microscale, we have a procedure in which we do the mesh of the microscale, and then we upscale the result. Once we do the simulation of the microscale, we took some samples of the microscale, and we have geometry, the definition of parameterized definition of the geometry, so we can generate for this type of geometry any turbolator with different thickness, with different step, so we can do easily whatever we want. And then with we can do the simulation. We proceed. We generate this mesh in which we have the fluid mesh and the solid mesh, and then we proceed with the simulation. The simulation is a very detailed simulation, since you see the resolution of the microstructure is quite well defined. So we have a grid that has, let's say, 100 of millimeter. More or less 110 to 100 of millimeter. So we use the representation simulation of a REV, so a representative element volume, and we simulate this, putting a kind of clusters of this element using a cyclic boundary condition. Cyclic boundary condition with source terms in the momentum equation to take into account the pressure loss that or the flow resistance that the flow feels when it crosses the microstructure, and also heat source term in order to establish an heat flux that reaches basically the expires the transient, so reaches the equilibrium situation. So in this case, what we have in terms of simulation is an analysis of what? Of the velocity field and temperature field. From the velocity and temperature field, we can also, from the pressure field, we can reconstruct all the characteristics. But the interesting thing is that since this geometry can be crossed by the flow in any direction, we have to perform the analysis of this representative element volume with different angle of the flow, so that we can have angle alpha equal to 0, so the flow is going from the left to the right, or we can have a different angle, 20 degrees, or here 90 degrees, so it is going from the bottom to the top in this case. And we have the representation for the same condition of the temperature field for, in this case, for a fixed velocity. But if we keep let's say the configuration fixed, we can vary not only the angle, but we can also vary the angle of velocity, but we can also vary the intensity, so the magnitude of the velocity, meaning the Reynolds number. So in the end, we can go from a laminar situation to a let's say a transient simulation where we have a kind of, it's not properly turbulence, it's a steadiness of the flow, and which forces us to perform a time average of the solution. And the final step of this is what? So similarly, we apply this to the dimple plate, changing the alpha and changing also the Reynolds number. And the final step is that we have tables in which we have the trend of the Colburn, of the fanning factor and of the Colburn factor, representing respectively the friction, so the pressure loss, and then the heat transfer, or the Nusselt number, in terms of as a function of the Reynolds number, and also as a function of the angle or incidence angle of the velocity. So this is a map that is used as a lookup table. For what? For the full-scale simulation. Full-scale simulation in which the turbolator, the dimple plate or the strip fins are basically not existent anymore, and there is just a porous media that represents the microscales, the subgrid element. And the resistance of this porous region depends not only on the Reynolds number, but also on the direction of the flow. So this forces the flow to follow the fluid, to follow preferential pathways in which the global resistance is reduced. So we can do this for the friction and for the heat transfer, and then we can pass from having these tables that can be assessed runtime in the simulation. We can pass from the microscale to the macroscale. If you can see from the microscale to the macroscale, what changes is the resolution of the turbolator itself. And here you see a 3D mesh, whereas here you see it's a 2D mesh because it has resolution in the X and the Y plane, whereas in the Z direction there is only one cell. So this reduces a lot the computational time required, and so also the cell count. You will see an example later on, and allows us to perform the simulation of a full-scale element. So predicting not only the thermal performance, but also the performance in terms of pressure loss, and allowing us to perform some optimization, so reduction of the size. Okay, so this is an example of how we apply this methodology. So we start with a base mesh that has a fully resolved mesh for what? For the dimple plate and for the turbolator region. We have here we have the base grid, and then we have a an agglomeration grid. So it's a background grid that is overimposed that tells how to agglomerate the small set that we have in the region of the turbulators. So in this way, we end up with a mesh that has a 1D resolution in the one cell resolution in the in the Z direction, and as you can see here, for this cooler, which is a cooler with 11 plates, oil plus coolant, starting from the base mesh in which the average mesh for the coolant, for the oil, and for the solid are around 15 million cells. So plus. So we are around 50 million cells. Well, we end up with something that has for the solid the same resolution because we are not reducing, agglomerating that mesh. But for the coolant, for the oil, we have a significantly lower mesh. So this is an advantage in computational time, which allows us to perform the full-scale simulation. So we have the big picture of what is the heat transfer inside of the cooler. Okay, and here the computational time for a fixed point, so it's steady-state simulation. Obviously, we have 6 hours on 6 processors for this simulation of this operating point. Okay, and here you see the 3 different regions. We have the solid, the oil, and the coolant, with also the inlet and outlet, the inlet and the outlet pipe, and as well for the oil. And this is say a cutting plane that allows us to see what is the temperature of the two fluids in a plane in which we have the inlet of the hot fluid and the inlet of the cooling fluid. So it's a kind of equicurrent with crossing between the two of them. So in terms of validation, we have validated internally in a collaboration with a group of our department. We have done the validation on different cooling systems, on different coolers, configuration A, configuration B. So we are just referring to the configuration A, which is the one that I have shown here. And we see that in terms of pressure drop, we have for configuration A, the red line is the calculated, the black line is the measured. Dots are the circles are related to the configuration A. So we have a good prediction of pressure loss for the coolant side and for the oil side, and also a good prediction of the thermal power for configuration A and configuration B, both for the oil flow side for the oil flow side, but for different flow rate, for different flow rate of the coolant. So what we have seen in this, coming to conclusion, what we have seen here in this presentation is a framework that allows us to perform the simulation of both the electrical motor with the production of heat due to the losses that are happening inside of the motor, the cooling system of the motor, and also the coolant, or also the cooling unit that usually performs the cooling of the oil that comes from both the battery and both the electrical motor in a battery electric vehicle. So for achieving this, we have implemented in the electrical motor a fully resolved solver in which we take into account moving mesh and electromagnetic effect along with the estimation of losses. And we have also parametric configuration that allows us to generate a mesh that is suitable for any electrical motor and also for the cooling unit. Obviously, it's a work in progress. There are a lot of aspects that must be taken into account. For example, for the electromagnetic phenomena, we have the back electric motor force, which is something that operates against the power that is produced by the motor. We need to play a little bit on the boundary condition of the vector potential in order to preserve continuity in the derivative, normal derivative, and discontinuity in the tangential derivative, but also in the representation of the windings. The windings here are basically region with a high thickness, whereas in reality they are just very small wires with a very low section, and this must be taken into account with with region models that are subgrid, working at subgrid level. Acknowledgement for the project that has funded this activity, which is a project that goes under the PNRR project funded by the European Union, and also a project funded by the Fondo per la Crescita Sostenibile, which is something related to the national national field, so not from the European Union, which is called CLIM, and has the objective of creating a unified cooling system with a unique cooling unit and a unique pump for the cooling system of electrical motor, batteries, and all the devices that need to be cooled in a battery electric vehicle. So I appreciate your resistance and resilience, and thank you very much for your attention.